So this lecture is looking at reaction rates and looking at something called a rate law. So as we're discussing in class, there are 4 different factors that can affect a chemical reaction. We have temperature, we have concentration, catalyst, and surface area. But the one that we could always change in a chemical reaction is concentration. So what we're going to look at is if we change concentration, how does that affect the rate of the reaction? So we are going to be talking about something called a rate law. Okay, but before we get to that, I kind of want to review a little bit of what a rate is. So again, rate is going to be change over time. So whatever that's going to be. And we are looking at things like deltas. Okay, so deltas are always going to mean change for us. Well, if we are looking at how something is changing over time, we are really looking at an inverse time relationship. Okay, so if I have a reaction, okay, that takes 45 minutes to make, let's say, a precipitate. So kind of like we saw with the thiosulfate hydrochloric, it turned cloudy. So let's say it took 45 seconds to get cloudy and you couldn't see the X anymore. Well, if I'm looking at a rate, that's going to be 1 over 45 seconds, 1 over 45 seconds. And so that's going to be, again, some kind of decimal, 0.022 or something like that, I think, when you divide that out. So rate and time are 2 different things. So if I want to make something go faster, okay, that's going to mean, let's say I am less than 45 seconds to get it to go to a precipitate. Well, the rate is going to be different though. So let's say it is 10 seconds, okay? So if I do 1 over 10 seconds, that rate is now going to be 0.1. Okay, so that's different in terms of, oh, it's 10 seconds to get to a precipitate, but the rate is going to be going faster. Okay, so again, it's less time to get to the final end, but the rate is going to be faster. So again, keep that in mind when we're talking about kinetics here. So if we are looking at changing concentration, we could write something called a rate law expression. So again, watch this video, take the notes as I go through it. And maybe after you do a problem or two, you might want to come back to this video where it makes a little bit more sense as to why I'm talking about this. So let's say I have a reactant A going to B, okay? I could write what we call a general rate law expression. Rate is always going to be on the left, and then this expression is always going to be on the right. So I'm going to have a little k, A in brackets, okay, A in brackets, which means concentration, and then to the power of M. And there, I don't know why they start with the letter M, but we don't start with A or anything like that. So we know that a chemical reaction, we're going to do rate is going to be molarity over time. So let's say it's for molarity over seconds. It could be molarity over minutes. It doesn't really matter. K, little k is called a rate constant. A in brackets is the concentration in molarity. And the exponent, M, can only be 3. These are the only 3 we're going to talk about, 0, 1, and 2. 0, 1, and 2 are going to be what we call 0, first, and second order reactions, okay? So what we are doing is we are changing the concentration of A and seeing how that affects the rate of the reaction, okay? So let's explain what the 0, 1, and 2 mean. Okay, so we're going to have what we call a 0 order reaction, a first order reaction, and a second order reaction. So M is going to be 0, M is going to be 1, M is going to be 2. And this is going to mimic what we have for, not mimic, but you are going to have the same math calculations as you would with an exponent. Okay, so if I have a 0 order reaction, if I have a rate law expression, rate is equal to K, A to the power of 0, we know that anything brought to the power of 0 becomes 1. Okay, so that means for a 0 order reaction, rate is equal to K. Okay, what you need to write down is rate is constant. So if you have a chemical reaction where the rate does not change, okay, that is what we call a 0 order reaction. So that means A has a power of 0, and you have something called the K constant that has a particular unit. I'm going to come back to the units when we actually work the problems. This is going to be just for some background information, okay? So again, 0 order is going to be the exponent is 0. If the exponent is 1, it's called a first order reaction. And so how this works is the following. Okay, so I'm going to write some data over here. So if I have a concentration of A and I have a rate, okay, if I double the concentration of A, what I'm going to do is write 2A in the brackets, 2A in the brackets. If I double A and it's a first order reaction, okay, whatever I do to A is going to happen to the rate. So that means the rate is going to go up by a factor of 2. Okay, so take rate times 2. That's what I'm trying to write here, rate times 2. Okay. If I triple A, the rate goes up by 3. So rate times 3, rate times 3. Same thing goes if I took it down by a half, my rate would decrease by a half. Okay, so first order reactions are the most common reactions that we have out here because in chemistry, because it is the most logical. Whatever I do to A is going to be what happens to the rate. Okay, so write down that this is the most common that you see in nature and in chemical reaction. Okay, and finally, the last one I'm going to talk about is something called a second order reaction. So that the exponent is going to be a 2. Okay, so I'm going to do same kind of idea over here. So if A, here's my concentration, the chemical reaction took place, I am looking at the rate. What happens if I double A? Well, in a second order reaction, it's going to have a 2 as an exponent. So just like we have a 2 on the exponent, 2 is going to be squared. So what are you going to multiply the rate by? 4. Okay, 2 squared. Okay. What if I tripled A? What is 3 squared? 9. So you're going to multiply the rate by 9. Okay, so whatever you do to A is going to be squared. Whatever you do to A is going to be squared. All right, and last thing on this video, if you have multiple reactants, A plus B goes to C, okay? A plus B goes to C. So you have 2 reactants. Well, A could affect how quickly you make product, and B could also affect. So A and B could have different orders. So A could be 0, 1, or 2, B could be 0, 1, or 2. So if we write out the full rate law expression, I have to include both reactants. So if I have A and B as first order, we don't write ones in chemistry. So what you will never see are the ones up on top here. So what you could say is it's first order according to A and first order according to B. And some worksheets will also talk about what we call the overall of the reaction. And that is when you add all the exponents. So this would be second order because you're adding 1 plus 1. It does not mean it's a better reaction. It doesn't mean it's more powerful. It's just a expression that you hear. So this one, second order according to A, first order according to B. This is first order according to A, second order. And again, all of this is going to be determined by what we call data. Okay, so this rate law expression is determined by data. So what we're going to look in the next video is how do we find the 0, first, and second order.